Hello, I welcome you all to my video lecture and myself C. Ashok Kumar, Professor, Department of Electrical and Electronics Engineering, and the course name is Electronic Device and Circuits. As you know, electronics is a branch of engineering or physics which deals with the motion of electrons in a semiconductor devices. And if you observe the syllabus of this particular course, the main important topic is the semiconductor physics. You need to know about the semiconductor physics, okay, before going to know about the principle of operation of the semiconductor devices, okay. So, by this course, we will be exploring the principle of operation of semiconductor devices and how they are used to build up the circuits, that means applications, and the student, whenever he completes the course, he will be able to know the principle of operation of the semiconductor devices and their applications. So for today's lecture, the overview will be like this. First, I will be discussing about this energy band diagram, by which we can classify the materials, and the second topic is the materials, how they are classified depending upon the energy band diagram. And then we will be taking the semiconductor materials and the types of semiconductor materials we will be discussing. One of the type is the intrinsic semiconductors, and finally we will be recapping the things. So energy band diagram, as you can see here, so this x-axis represents the interatomic spacing among the atoms of the silicon or any crystal or any solid, and this y-axis is the energy level in terms of units or in terms of electron volts. As you can see here, two bands are there. One is called as the valence band and second one is the conduction band, separated by the forbidden energy gap. Forbidden energy gap means it does not contain any energy levels. So valence band contains so many discrete levels which are closely associated with each other. That's why we will be calling it as a band. Similarly, in the conduction band also so many discrete levels will be there which are closely associated. That's why they are called as a band. So this is valence band and this is a conduction band. All the valence electrons of an atom will be contained in the valence band. Okay. Whenever they are excited to move the conduction band where they become free, the free electrons will be in the conduction band, by which the conductivity happens. So, before going into it, let me discuss about how the energy bands are formed inside a solid. So, I am taking the silicon solid here. So, that's why here I am taking a silicon atom. So, this is a Bohr's atomic model. This is a nucleus, and if you observe the silicon atomic number, that is a 14. And if you write the atomic electronic configuration, so it can be written like this: 1s2, 2s2, 2p6, and 3s2, 3p2. Okay. So this first shell, that means here, as you can see here, this is a innermost orbit. Okay, so innermost orbit means, as you can see, the electrons which are contained in the innermost orbit are closely associated with the nucleus. Okay, so 1s2 means how many electrons are there in this particular shell, first shell? 2 electrons are there, as you can see, 2. And in the second shell, which is a combination of 2 subshells, one is S, second one is a P. So 2 plus 6, 8. As you can see here, 1, 2, 3, 4, 5, 6, 7, 8. So the second shell, second orbit contains 8 electrons. And if you observe the influence of the nucleus upon these electrons, so they are attracted towards the nucleus. Innermost orbit and next orbit electrons are attracted towards the nucleus. Okay, what about this third orbit, third shell? Once again, it contains 2 subshells. The total number of electrons are 2 plus 2, 4. As you can see here, 1, 2, 3, 4. So this particular shell or orbit is called as outermost orbit. Outermost orbit means whatever the electrons that are contained in this particular orbit, they are called as a valence electrons. Okay, so the nucleus influence is not there upon these valence electrons. Why? Because they are in the outermost orbit. Okay, so these are called as a valence electrons. If you observe this valence band, the valence electrons will be contained in this valence band. Okay, so now let us discuss about how this energy band diagram is formed in a solid. Let us take a silicon solid. As you know, the silicon solid contains 10 to the power of 23 silicon atoms per cubic centimeter. So more number of silicon atoms will be contained in the silicon solid. Okay, so by the attraction among these atoms which are neighboring with each other, so some formation of bands will be created inside the solid. How it happens, let us see. So as you can see here, 1s2, 2s2, 2p6. These are, first one is the innermost orbit, next neighboring orbit. Here all the electrons that are contained will be influenced by the nucleus. Okay, we won't concentrate on this. And here valence electrons, outermost orbit, 3s2, 3p2. Okay, so now let us see what happens here. So at the beginning they will be at discrete levels. Okay, assume that the total number of atoms of silicon in the solid be n, capital N. Okay, so here as you can see here, what is this A, B, C, D? This axis I already said, that is the interatomic spacing. Interatomic spacing. So many atoms will be there inside the solid. So depending upon the spacing among them, some physical changes happens inside a solid. Okay, so that's why here whenever at R is equal to D, whenever interatomic spacing is somewhat large, whenever you move from left to right, the interatomic spacing goes on increasing. Whenever you move from right to left, the interatomic spacing goes on decreasing. Okay, so that's why here at D, both are at discrete levels, 3p2 and 3s2, right? At R is equal to C. R is equal to C. Let us check the status. Status in the sense, if you observe this level, energy level, how many allowed states are there and how many occupied states are there, how many electrons are there in the occupation. So let us take 3s2. Okay, so 3s2 means how many states are there here? S subshell. Okay, S subshell means 2n states are there. How many electrons are there here? 2n electrons are there. Okay, and what about this discrete level? I am talking the situation at R is equal to C. So the subshell, P subshell, that means how many allowed states will be there? 6n. And how many occupied electrons are there? 2n electrons. Okay. Okay. So at from R is equal to C onwards, what is happening here? This discrete level is splitted here, and this discrete level is splitted. And at R is equal to B, at R is equal to B, what is happening? They are splitted and they are combined here. They are combined. So whenever they are combined, what is the status here? So status, how many allowed states are there? Total allowed states here 6n and here 2n. So 8n allowed states are there. And how many electrons, occupied electrons are there? 2n plus 2n, 4n electrons are there. Okay. So I am saying about the status at R is equal to B. Okay. Whenever at R is equal to A, at R is equal to A, the value, typical value will be 2.35 angstrom units. And 1 angstrom unit is equal to 10 to the power of minus 10 meters. Okay, at R is equal to A, where A is equal to 2.35 A, what is happening here? After merging, they are separated equally into two bands at r is equal to a. Okay, so first they are splitted and then they are combined, and here they are separated equally. They are separated equally. So let us discuss about the status here. So equal separation means total allowed states are 8n. So here 4n I am writing allowed states. Similarly here 4n I am writing. But here kindly keep in mind the total number of electrons will be contained in this valence band. So here I am writing 4n electrons. And what about the status in the conduction band? Here it will be 0 electrons. Okay. So this upper band I am calling it as a conduction band, and the lower band I am calling it as a valence band. So valence band always it contains filled electrons which are filled by the valence electrons, whereas the conduction band is empty. Okay, conduction band is empty at the beginning. Okay, valence band contains a partly or filled, whereas conduction band is empty at the beginning. Okay, so in this way the energy band is formed inside a solid. I have taken the silicon solid. So at the beginning they are at discrete level, and then they are splitted, and then they are combined, and then they are separated. Separated equally. Upper band is called as conduction band, lower band is called as a valence band, separated by the forbidden energy gap. Forbidden energy gap means, kindly keep in mind, it does not contain any energy level in this particular gap. Okay, depending upon the size of this energy gap, the classification of material happens. Let us see the next slide. So this is about materials, how the materials are classified based on the energy band diagram. Okay, so first let us take about the insulators. So as you can see here, this is a conduction band and this is a valence band, and here the forbidden energy gap is very large. Okay, so you need an energy of 7 electron volt for an electron from valence band to jump into the conduction band. So first of all, how the conduction happens inside any device means, whenever the electron from valence band is jumped into the conduction band, so it becomes free here. It becomes free to wander. Okay, whenever the movement of electron happens, that contributes to the flow of current. Okay, whenever the electron from valence band is jumped into the conduction band where it becomes free to move, then only the conductivity happens. Okay, as you can see here, the band gap or forbidden energy gap is very high. So that's why there is no chance of any electron to move from valence band into the conduction band. Whenever there is no chance of any movement of electron to jump into the conduction band, then there won't be any conductivity. So that's why here the insulator conductivity is very poor. Why? Because no chance of any valence electrons to jump into the conduction band. Why? Because the forbidden energy gap size is very high. We need a larger energy to move from valence band into the conduction band. That's why the conductivity is poor in the insulator, and the example is wood. Okay, next let us take the conductors. As you can see here, if you observe the energy band diagram, the energy band gap is not there here. They are both are combined with each other. So that's why here whatever electrons that are there in the valence band, that will be in the conduction band. So that's why here a larger movement of free electron happens in the conduction band, that contributes to the flow of current in a large manner. That's why the conductivity with the conductors is very high. And example is the copper. Okay, and our targeted material, semiconductors, which is intermediate between insulator and conductor, right? So here the band gap is very small. The energy required is 1.1 electron volt. So the electron from valence band needs an energy of 1.1 electron volt to jump into the conduction band, where it becomes free to wander, which in turn creates the conductivity. Okay. So if you observe the semiconductor at 0 degree Kelvin, okay, so there won't be any chance for valence electron to jump into the conduction band at 0 degree Kelvin. Okay, So no conductivity happens. So that's why here the semiconductors are called as insulators at 0 degree Kelvin. Whenever at room temperature, let us take a room temperature. That means if you talk with respect to absolute temperature, it will be 300 degree Kelvin. If you talk with respect to the Celsius, 27 degree Celsius. Okay. So there what happens, the thermal energy inside the device will broke the covalent bonds, by which the electrons in the covalent bond will come out. In other words, we can say like this: the valence band will be jumped into the conduction band by the thermal energy at room temperature. Whenever it is jumped into the conduction band, here the electron will become free to band, which in turn creates the current. So the conductivity happens only at room temperature. At 0 degree Kelvin, no conductivity happens. So if you observe the classification of semiconductors here, they are divided into two types. If you talk the semiconductor in its purest form, it is called as intrinsic semiconductor. And if you talk the semiconductor in its impure, that means if you dope any impurity into the system, that is called as extrinsic semiconductor. Once again, they are divided into two types that will be discussed later. So intrinsic semiconductor. Intrinsic semiconductor, as you can see, this is an isolated silicon atom. 4 valence electrons will be there. If you observe the silicon solid crystal lattice structure, as you can see here, all the silicon atoms are making the covalent bonding with the neighboring silicon atoms. So this valence electron of silicon atom is making the covalent bonding with the neighboring silicon atom like this. And the valence electron of this silicon atom is making the covalent bonding with the neighboring silicon atom valence electron. Similarly here, this silicon atom valence electron is making a covalent bonding with the valence electron of this silicon atom. In this way, the covalent bonding happens inside the silicon solid. Okay. So same explanation. As you can see here, these are the covalent bonds which are formed by the neighboring silicon atoms. And this is the energy band diagram. As you can see here, this is a valence band, this is a conduction band, and EV is the highest energy level in the valence band, and EC is the lowest energy level in the conduction band. And this is the band gap. So whenever at 0 degree Kelvin, it behaves like an insulator, nothing happens. No valence electron will be jumped into the conduction band. That's why the conductivity will be equal to 0. At room temperature, what is happening here? It is shown symbolically like this. Thermal energy is created, which is affecting the covalent bonds here. The covalent bond is broken here. One electron is coming out. This can be represented in the energy band diagram like this. The electron from the valence band is moved to the conduction band. As you can see, it is free to wander, which contributes to the flow of current. So here, one more charge carrier along with the electron, hole also contributes to the flow of current inside the intrinsic semiconductor. So how it happens, let us see here. So this is valence band and this is the conduction band. Whenever the electron, first here the valence electrons will be there. So whenever it is jumped here at room temperature, here a vacancy will be created. Okay. And here it will be wandering there in the conduction band for some time, contributing to the flow of current for some time, after which it will be once again falling back to the vacant space in the valence band. That is called as a recombination, and this process is called as a electron hole pair generation. Electron is moved here, electron is generated, which in turn creating a vacant space that is nothing but a hole. Okay. Whenever hole is created here, the neighboring electron will be moved into the hole like this, once again creating a space here. So here a space is there, the neighboring electron will be moved into this space, occupying, once again creating a space. And here once again the neighboring electron will be moved into the space, creating a space. So in this way, the motion of hole is also happening here. At the beginning, the position is here. Next it is moved to here. Next it is moved to here. Next it is moved to here. So the whole movement is also happening here, along with free electron movement in the conduction band. Okay. So the total conductivity in the intrinsic semiconductor is by the movement of free electron in the conduction band and by the movement of hole in the valence band. Okay, the contribution is made equally both by this charge carriers. One is electron, free electron in the conduction band and hole in the valence band. So how it happens, how the hole is contributing to the flow of current, let us see here. So here a vacant space is created by the ball 1, which is occupied by the ball 2. So that's why here the space is moved here, vacant space, and the third ball is entering into the this vacant space, creating a space here. So the positions are changed here. First the space is created here, next it is moved to this position, next it is moved to this position, like this. So in this way the whole motions happens from left to right. Okay, so that's why here along with electrons, the holes are also contributing to the flow of current. So the flow of current is both by the two charge carriers. One is by free electrons in the conduction band and by the hole movement in the valence band. Okay, so the disadvantage with this intrinsic semiconductors are, as you can see here, the number of free electrons count is very less. So for electronic applications, whatever conductivity happens with this intrinsic semiconductors, the value is very small, which is not suitable for the electronic applications. So that's why here we will be going for other types of extrinsic semiconductor, where we will be increasing the conductivity by doping impurity into the system, by increasing the number of free electrons in the conduction band, or by increasing the number of holes in the valence band. That will be discussed later. So I will be stopping here and I will be continuing in the next lecture. Thank you.